Hi there guys, so this is 8G and this is using complex numbers and matching the ideas of complex numbers up with trigonometry. Okay, now this is a difficult double page to get your head around, and there's no little box at the end of it, no sort of pink box that says this is what you should learn. There's a little hint to the side, but there's just an investigation. So the investigation is really worth doing here. Now I'm going to do the part where in the second bit, just go with me here. So I'm going to go through part 8 here, so the sort of general version. And in fact, part 8 is essentially what you need to learn. Those are the formulas which you need to apply. So that's the generalized version of what they do in a specific version throughout these throughout this investigation here through the other parts. Okay, so I'm going to basically prove part 8. Okay, and then there's just one question here, and it starts talking about voltages and phase shifts and amplitudes and frequencies and so on. And so there's quite a lot to unpack here. But if you just want to learn the formulas from 8 and then go straight onto the example for 10, that is fine. But I'm going to go through unpacking how to prove part 8 to start off with. Okay, so what is this all about? So this is about adding together two sine functions. That's my way of saying functions here. Adding together two sine functions with the same frequency. So here we go. Here's f of x and here's g of x, and they have the same frequency. The frequency is a. That tells you the horizontal stretch that we're applying to the sine function. So there's also a translation which is happening here as well. But yeah, the A here is talking about the stretch. That's talking about the frequency of the function. So in this case, we're always talking about the same frequency. So so we don't need to worry about that really, but we can just kind of leave this A in here and here. Now, we're going to end up with one sine function. So when we add together this sine function and this sine function, you'll end up with another sine function, which they're calling here r sine A x plus alpha. Now you'll notice, of course, we've got the same A here. That's the same frequency as these two. But we've got here R instead of R1 and R2. So this is just another constant. In fact, the way in which we find that constant by doing this. And again, I'll talk about that in a bit in a while. And then the phase shift is this, and that's again a combination of using the other R's and the other alphas here. So alpha 1 and alpha 2 and the other R's. Now, if you just want to use this formula here and this formula here to find your amplitude, so R is amplitude, pointing at here, R is the amplitude. And if you want to find the argument, or in other words, what they're calling the phase shift here, so the angle which is the phase shift, in other words, the translation which is happening to a combination of the two sine functions, which is giving you one sine function here. So this translation here, if you want to find this, that's the same as working out the argument of these two complex numbers added together here. Okay, so let's just recap what we're talking about here. We've got two sine functions. We're adding them together. We get one sine function. We no longer have R1 and R2. We just have R. We no longer have alpha 1 and alpha 2. We have alpha. And we find the alpha and we find the R through this formula here and this formula here. The alpha, in other words, the translation of this sine function, and by the way, normally we'd do that translation in terms of ax plus alpha over a. That's how we normally deal with the transformations, but we're just talking about this thing being called a phase shift, and it is going to have an effect of a translation. And that translation is not necessarily the alpha there, by the way. It's going to be the translation of x plus alpha over a. There's the actual translation, and it's acting in the opposite direction, but that comes from functions. but this is having the effect of some sort of translation, but we're calling it its phase shift. Okay, so yeah, if you want to find that phase shift, then you need to use this formula, and if you want to find this R, then this amplitude, then you can use this formula here. Okay, if you want to switch on now, if you want to move on to example 10, then just move further on into the video. What I'm going to prove now is that this is true. Okay, that it is true that when you add together two sine functions with the same frequencies, then you're going to get another sine function with the same frequency, but with a different, what's called phase shift, and a different amplitude. Okay, so let's get rid of all of this, and let's take this, first of all, into complex numbers. Now, what I'm going to do is actually start the wrong way round. So I'm going to say, let's put the complex number in Euler's form. Say we've got R1 here, and E A X I, then E alpha 1 I. And I'm going to show that this is the same as this. Okay, so it's going to give us this thing here. So this is going to be an alternative way of finding out f of x. That's another way of defining f of x. And if we can define it like this, then we can start working in terms of complex numbers. Okay, so let's just show that that is true. So I'm starting the wrong way round here, but this one here, we could say, well, we can use the laws of indices to combine the two exponentials e to the power of these two functions here. We can combine those two by adding together those two powers. So that's what to start off with. So we've got the imaginary value of r1 e to the a x plus alpha 1 I. Okay, so now I've just brought those together as well. So I've basically added those two powers there, but I've also factorized out the I as well. And now if we're going to do the imaginary part of this, well, that's the same as saying the imaginary part of, let's put this into its other polar form. So let's put it into cis theta. And so in this case here, we're now going to get R1, and this is going to give us here cis theta. So that's going to be cos of ax plus alpha 1 plus I sine of the same thing here. That's like your theta, if you like. This is ax plus alpha 1 there as well. Now, if we take the imaginary part of this, that isn't this part, it's just this part here. Now you can see that the imaginary part is just this part without the I. So you're saying that's R1, it's still being times by R1. And then we've got sine of ax plus alpha 1 there. Okay, so we've now shown that this is the same as this thing here. Okay, so now obviously we could do exactly the same thing for g of x. So we've got here that this is now equal to f of x. Let's just highlight the fact that we can use this now, and we can do exactly the same thing for g of x. Now, if we do the same thing for g of x, this is going to change to r2, and this is going to change to alpha 2. Okay, now if we want to add together f of x and g of x, and let's call this h of x, which is what was happening earlier on in the investigation here. So we just call this another function. So our h of x here is going to be equal to the two functions added together. Well, that's going to be the imaginary part of this one added together to the imaginary part of the other one. So we've got here h of x is going to be the imaginary part of this r1 e to the a x I e to the alpha 1 I plus the imaginary part of this thing here, essentially with r e to the a x I, but with r2 there and e to the a2 I. Now we can actually combine both of those two things together, no problem, because essentially this is just r cis theta. We've got another r cis theta, but they both expand out. and the imaginary part of one added to the imaginary part of the other is just the same as the imaginary part of the entire expression, because there's two separate imaginary parts which we can then add together. So that's not an issue here. If you want to expand that one out, of course you can, but it's fairly easy to see that this is e to the axi again, and then e to the alpha 2I. Okay, so again, that's just imaginary part of this plus the imaginary part of this, but we can take the imaginary part of the entire thing as well. These are just terms which are added together when you expand this out to r cis theta and r cis theta again. Okay, so then we can do a little working out inside here. So we can say that this is imaginary part of now. We could factorize out the EAXI, and inside we're left with R e to the alpha 1I plus R2 e to the alpha 2I. And that I is not, let's just take it back and make it a little easier to see. So this I here is not a subscript here, it's just a full letter here, timesing by alpha 2. The 2 there is a subscript. This is not a subscript. The reason why I say that is because often we're talking about, say, for example, if we say UI, that might be a term in a sequence, and we'd normally use the subscript. It is not a subscript in this case. I is your complex number. It's the square root of -1. Okay, so this is, now we've got h of x is the imaginary part of this complex number here, and then we have a complex number plus a complex number, which gives us another complex number, and we could call that complex number inside, so the imaginary part of EAXI, and then this one inside could be a complex number RE to the alpha I. Okay, and then close that one off. So now what we've got is we're saying that these two complex numbers here can be combined to make one complex number with the magnitude, so it's the size of that complex number being r, whereas previously we had two complex numbers of size r1 and r2, and the direction of that being alpha, whereas previously we had two complex numbers with two different directions. Now we've combined them, so we've combined two complex numbers. So here's one and here's one. We've added them together, and that would just take us up to sort of here. This would be the same as this length here. So the resultant of those two take us up to this complex number here. Okay, now that complex number has a particular magnitude, and that would be r. This would be r1, and this would be r2. And the angles of those two, so this has a particular size, and the angles of those two would combine together in some way to work out the angle for this complex number here as well. Okay, now you can see you could go back into your Cartesian grid there, but we can work in this polar form, in this Euler's polar form. So we can already work in this form to say, well, if we can work out the argument of this complex number, we could do that on a calculator. We could just say, what's the argument of this thing here? That's going to give us the argument of this thing here, so it's going to give us this. And what's the modulus of this thing here? It will give us just the r here as well. So I'm skipping a little bit of algebraic working out here, because it is sufficient to say, and sufficient for us now to say, look, we've now made h of x into one function which looks like this. In other words, it must be a sine function, like this one was. Whereas now we don't know what r and alpha is, whereas we did know r1, alpha 1, and r2, alpha 2 there. But now we've made another complex number here. And we're saying, well, the size of this complex number is going to be r, and the modulus, sorry, the modulus is going to give us r, so the absolute value is going to give us r. And also the phase shift is going to come from the combined phase shift of these two complex numbers here. Right, okay. Now you might be thinking, hang on a second here. R is you're saying that R is, we've got here the imaginary number. The imaginary part of this complex number is R, but that's the imaginary part of this complex number. So is it really R for the entire thing? So here we had R outside the front. It's very easy for us also to say that's equal to imaginary number of R e to the AXI times by e to the alpha I. So the imaginary part of the entire complex number here, which is what we were saying here, the imaginary part of this was the modulus of the entire complex number here, rather, is the same as the modulus of the entire complex number here. So we can simply say, let's take the absolute value of this, and that will give us the R that we require. And that's the same as saying, what's the absolute value of this, or the modulus of this? That's making some sense there. The modulus of this give us R1 in this case. The modulus of this will give us R in this case, but that's equivalent to saying the modulus of this, because we've just factorized out the R, because this one had a size of 1. Okay, I'm just going to take that back a little bit. Hopefully that's kind of obvious. Okay, and so what we're leading to now is saying, well, here we go. We're saying, if you can take the modulus of this, then that's going to give you R. That's what it's saying here. So the size of this complex number is the modulus of this complex number, and that's R. And that's also the modulus of this entire complex number here, which is this R here. So that's where we're getting this formula from. We're saying now the modulus of this gives us R, gives us one complex number which we can find the modulus of. Okay, so that's where this comes from. And then it says, what's the argument? What's this alpha? This here, alpha here. Well, that's the same as the argument of this complex number. The argument of this complex number, which is a combination of these two, is the same as saying what's the argument of these two here. So that's where this is coming from here. Okay, right. So now we need to put this into some sort of context. Now I am aware that that proof was kind of challenging, but I think you can at least hopefully agree that the imaginary number, the imaginary part, I keep saying imaginary number, the imaginary part of this complex number here is this. So we can write sine functions with amplitudes here, frequencies, and phase shifts, as we're defining these things to be, which do amount to some sort of translation, in fact, but not the translation of alpha 1. This can be written in this form here. If we can write it in this form here, we can do the same with g of x here as well. If we then combine those two things, we can then say that comes up with our alternative format here for this thing here. That's the imaginary part of this complex number here. And then we're saying, well, okay, well, what's R? Well, R is going to be so what's R in this case? Well, that's going to be the same as the modulus of this combined complex number here. That's where we're getting this from. And we are doing if you want the argument of this thing here, that's the same as doing the argument of this thing here. Okay, hopefully that is all sorted out. Okay, so let's have a look at the question then. So, and let's try and just copy those formulas in as well as we're doing this, so that we've still got them. Okay, sorry, that's not going to work. Do that one again. Okay, so this one is saying that we have a voltage of an AC electrical source modeled by the equation, and they're putting it in terms of a sine function. By the way, even if it was a cos function, cos functions and sine functions, whatever you've got, this could be written in terms of a sine function by certain amounts of transformations. So we can write any wave in terms of sine or cosine, it doesn't matter. So if we choose to write them both in terms of sine, if we've got these two functions which we're adding together, then it just makes it easier and we don't need to worry about the cosine version. Okay, so there's your V for the first one. This is voltage. And it says C is the phase shift. That's how it's being defined to be. And two AC sources with equal frequencies, so the B is the same, are combined. One has a maximum voltage of 80 volts. Okay, so when we're thinking about this sine function, maximum here is 80. Now there is no plus or minus anything off the end here. It is just oscillating about the x-axis here. So we know that the amplitude is not 1, which would be our normal sine function, but it is 80. So the entire function has been stretched in the y direction by a factor of 80. That means to say that A is 80. Well, one is 60 and one is 80. Okay, so one is 60 and one is 80. Now, the amplitude of the sine function gives the maximum voltage of each electrical source. First electrical source has a phase shift of 30 and the other has a phase shift of 120. So that's this part here. So let's write those two things out. So we have V1 is equal to 60 sine, and we don't know what B is. But we don't care about what B is as well, and that's T in terms of time. And we have plus C, and C here is equal to 30 degrees. Everything is in terms of degrees in this question, not in terms of radians. So we need to make sure that our calculator has that in its settings, in the document settings. And V2 here is equal to your 80 sine dt plus 120 degrees. Okay, find the maximum voltage in the phase difference of the combined source. Okay, so we're going to then combine these two functions here. What we're going to try and do is do V1 plus V2. Now we can't just combine these two things here because they are happening. So let's just put one, and we've got another one. Maybe it's going like it's got the same frequency. So maybe it's going from here to here. It's got a different amplitude. So we might be adding this one here. So we're adding these two functions here, roughly speaking. Okay, and when we put them together, we get one sine function. But at no point are we going to be adding the maximum height to the maximum height of the other one. In fact, we definitely know that the amplitude is going to be less than 80 plus 60. It's going to be less than 1/4. But at some point when we add these two together, we'll get a maximum point. So it looks to me like we're adding together maybe something over here with something here, and that might give us our maximum point. So it might be up here. So I'm just making up these two here just to sort of demonstrate what's going on. Okay, so find the maximum voltage. So what do we need to do? We need to add together these two things here. Now, when we add them together, we've got this. We're talking about getting the imaginary part of, we're getting e to the I A, and A was essentially our B, that's the frequency, so we're getting Bx, and then inside the brackets we're getting R1, so R1 is 60, and then that's e to the I alpha 1, which is 30. Maybe it's neater if we say 30i. And then we've got plus R2, so we've got 80 e to the 120i. Okay, so that's what we've got. And I've just sped things up a little bit here because it took me some time to write this one down here. Let's put that on the end again. It took me some time to write this and took me some time to write this, but essentially this is now using the formula here and using the formula here. We are working out the size of the amplitude of the combination of the two functions. So putting these two functions together, we're working out this with this formula here. And that is just putting this in this format here. If you want, you can completely bypass this And if you learn these formulas, then you can use this and you can use this. Okay, so that's what we're doing now. Now, in fact, if I was writing this onto a calculator, probably what I would do is store this thing here, store this complex number here to start off with. So, and we don't need this, of course, because we don't actually know what the frequency is. So just this complex number inside. So we can call this thing here, store it as Z potentially. So store, so we do that on the TI Inspired by doing control and variable. So we can store that as Z, and then it will be much easier to do modulus of Z and also the argument of Z as well. Now on your calculator, one thing to note is that if you're typing all of this in, when you come up with the modulus brackets first, because it will give you a space to put something in the center. If you type all this out and then you want to do the modulus of it, then you'll need to do abs, put brackets around it, and then that will change it into the modulus as well. Because when you type in the modulus, if you type lots in, and then you try and type the modulus in front, you'll have something inside, and you want to get this whole thing in there. So a way around that is to say, instead you can say abs, and the absolute value, and then do the brackets instead. Okay, and also to find the argument on your calculator, it's angle. And probably your calculator is set up in radians, although this is all in degrees. And if your calculator is giving answers in radians, there is no problem with that. We know that if we wanted to change, say for example, let's just go with the classic one. We've got pi is equal to 180 degrees. So if we wanted to change 180 into pi, we'd need to divide by 180 and then times by pi. Well, that's the same as timesing by pi over 180. So if we want to go from degrees to radians, this is what we times by. If we want to go backwards the other way around, we times by 180 and divide by pi. Okay, and that might be quite useful because if you've got your answer in radians, we can switch that quickly into degrees. And I think the reason why I say that is I think that in terms of complex numbers, I think it will always be set up in terms of radians. I'm not sure on that, but I think that's the case. So, right, so there we go. Let's have a look at the answers in 1 second, but also let's just see that they do say to find the phase difference. When they say the phase difference, they don't mean the difference between these two things here. They're still meaning the phase shift. I really think they should say the phase shift there. So that's certainly what they're working out in the question. So the phase difference of the combined source, the phase difference, that is to say from the original sine function, not phase difference between these two functions, the difference between those two numbers. Okay, so phase difference of the combined function to the sine function is just the phase shift. That's what they want. Now, if we have a look in the book, oh, by the way, in a second, I'm going to just show you this on the graph. So I was just getting up as well. And if we look at this in the book, they're coming up with the phase shift as simply as the argument there. Yeah, they're not doing a difference. They're just working on the phase shift. Okay, so that's pretty straightforward. Let's look at if you go to click on the calculator button, then you'll see how this is done on the calculator. And we've basically done this before, I think, in previous questions. Simply the amplitude of this complex number when combined. And again, to find that, you can do the modulus sign, or you can just type in abs of that complex number. And I would store that complex number there as something or other. And then if you want to work out the angle, you go to number, complex number tools, polar angle. And so then you type in this, and again, if you've saved that as something or other, stored it as Z, then you can say polar angle of Z. Okay, so I also wanted just to look at a couple of these questions, at least some of them. There's only 5 questions here. Again, I would suggest getting maximum practice with this. They talk about electrical currents, again, with question 1, question 2, and question 3 there. Question 4 is just more theoretical. And question 5 is quite nice, and it's not obvious that you need to go into complex numbers for this. But let's have a little look at question 5 here. Okay, so for question 5, in the exercise 8G, they're talking about two formulas, and they're saying here we've got the function for the time of sunrise and we've got a function for the time of sunset. Now the hours of daylight is going to be this one, take away this one. I mean, fairly obviously. So you're going to need to do G of t minus ft. Now that's the same. That's going to be the same as adding two sine functions. Subtracting two sine functions is exactly the same. Okay, so in this question, you're going to end up getting, you'll get definitely this number take away this number, no problem. Sorry, wrong one. This number take away this number, no problem. That gives us this 12.03 at the end. But then our problem is to subtract these two sine functions, and you'll notice, of course, they have the same frequency in this case. So this is what's alerting you to the fact that we need to go through this complex number method. Okay, so when we do that, that's obviously going to give us 2.19 sine of 0.0165 t minus 1.23, and subtract this part here. Now, again, the numbers at the end are just this, take away this, so that's not particularly interesting. It's the other part, which is a combination of the two sine bits, which is going to be challenging here. So, and then we take away 2.14 sine of 0.0165 t plus 1.81 there. Okay, so that's what we've got to figure out. Now, that's obviously the same as saying plus minus. So what we can do is incorporate the minus into this value here. So that becomes your R2. Your R2 is essentially just negative in those formulas. Okay, so then we can use the formulas as before. And again, then we're simply going back to these formulas which are given. So we've got, again, we want to work out the modulus of R1 e I to the alpha 1 plus R2 e I to the alpha 2. And again, the argument of that complex number as well. And it's just to note that R2 is going to be negative in that situation. Just adding a little bit on the end here, because I forgot to show you this thing here. So just adding those two functions together from the question, there was one of the functions, there's the other function. You can see that if we change the frequency, you know, that we've got the two things expand at the same sort of rate. So the frequency is the same for both of them. Let's actually just set them both to 1. And I mean, you can see that this frequency here, if b is equal to 1, that's actually going to give you from 330 to minus 30. That still gives you your frequency of 2 pi or 360 degrees. So you can see that b just tells you how often this is going to, how many repetitions you're going to get in 360 degrees, essentially. So it's going to happen once in 360 degrees. And that's the same for the other one as well. So there we go, it goes from 60 to 420. So again, that's happening once in 360 degrees too. Okay, now if we add those two things together, so if we say we've got f of x plus g of x there, you can see that we're getting another sine function. So that's just verifying that we are getting one other sine function in this case. And well, there you go, that's it. So, and you can see perhaps as well what I was talking about earlier, that if you've got two sine functions, you're adding them together, then it's not true to say that the amplitude is just going to be the 80 plus the 60. So the amplitude of the green one plus the amplitude of the red one, which would be 140. In this case, it's giving us the amplitude of 100, which, let's have a look at the book again. So again, that was our amplitude in this case, and the phase shift of 83.1. And just to show you, the phase shift of 83.1 is here on this graph, but that's not necessarily the translation of the sine graph. So this black sine graph is saying, well, we're translating it backwards by 83.13. But obviously, if we go up to 2, then because the stretch is happening after the translation, because the transformations inside your bracket's always the opposite way around, then that's coming into half of your phase shift there to this point here. So what I'm talking about here is if we've got hx is equal to r sine ax plus alpha, this phase shift is not the same as the translation, which I think is what I mentioned earlier on. If we want to know what the translation is, we need to factorize the thing inside. So x plus alpha over a. So for example, if we wanted to make A2, which is what we've just done here, so I've just made B2 there, same. Then we can see that the translation of this sine graph is going backwards by half of the phase shift there. And then we can see that if we made this equal to 2, then half of this would give us the translation of half of the phase shift again. So again, phase shift is different from translation, but it's definitely related to it. Okay, right, that's all I wanted to say on the graph, I think that's all I wanted to say. And also I wanted to say that in the formula booklet, that this does not turn up. I've just checked on this one. You have to remember both of these rules. So you're going to need to learn both of these things. And again, let's just point those two things out. So you're going to need to learn this formula here and this formula here. They do not turn up in the formula booklet. Okay, guys, well, thank you very much for listening in, and good luck with the exercise.